In the next few video chunks, we're going to start looking at a type of model called Markov models. And in this chunk, I'll talk through the basic mathematical setup for Markov models. And in the subsequent ones, we'll talk about two particularly pervasive examples of these models. So the idea behind Markov models is to write down a really simple structure that can be used to model sequences. So in this next section of the course, I'm going to denote the sequence that we're looking to model, the observed data, y1 through to y big T. So we're going to have big T, a sequence of which is of length big T time steps. And often you might see me abbreviate this using what's sometimes called MATLAB notation as y subscript 1 colon T. And this just means all the variables from 1 to big T in the sequence. Now, a general model for a sequence like this would involve writing a probability distribution over the entire sequence. So that would be a distribution over variables y1 through to big T. And what a Markov model says is we won't be modeling all of those dependencies. We're going to simplify things down so that each item in the sequence, say y3, is just dependent on the preceding one, in this case y2. Or at the end of the sequence, for example, y big T will just depend on yt minus 1. And so this is quite a restriction. In general, we know that yt here could, at least in principle, depend on all of the previous items in the sequence, y1, y2, up to yt minus 1. But we're going to say, no, we're going to ignore or not permit any dependence on items earlier in the sequence. We're just going to allow you to generate the probability of the next item in the sequence given the previous one. And this is what's called a first order Markov assumption. And we'll talk in a little bit more detail about exactly what that assumption means in a second and how restrictive it is. This model can be sort of handily represented using what's called a directed graphical model. Directed graphical models don't just apply to sequences, but they're particularly useful for showing the assumptions that we're going to make about the sequence in a graphical way. And that's what's shown below here. So in this graphical model, the rule is quite simple. You have a circle for every variable node. And here, of course, we have big T variable nodes, y1 through to yt. So we lump down our variable nodes. And then if we take a variable, let's say yt, and we look and see what does the probability of yt depend on, and it only depends on yt minus 1. So we draw an arrow from here, yt minus 1 to yt. And similarly, y3 only depends on y2, so we have an arrow between those two variables, and y2 just depends on y1. And y1 doesn't depend on anything else. Okay, so this is a representation of this distribution over sequences. And this is going to be kind of useful for showing in a parsimonious way different models as we go through this section of the course. So one way I like to think about this model is it's doing something kind of neat for us. And the reason it's going to do something kind of neat for us is the following. In general, we might use different parameters, say for this distribution and this distribution. Okay, so we could in principle have a different distribution for y3 given y2 as opposed to y2 given y1. And similarly, we might have a different set of parameters for this one as well. And that would mean that as the sequence grew in length, we would end up with more and more parameters. The number of parameters would scale like big T. And that is a bit cumbersome. And unless we have multiple sequences, it's going to be hard to learn anything meaningful from that. And so the neat thing that we can do using a Markov model is we can tie the parameters together. We can say all of the parameters, theta 2, theta 3, theta t, they all equal the same parameters theta. So we'll lose this time dependence on these distributions. So the distributions of the next item in the sequence, given the previous one, we're going to assume is fixed. We don't have to do that, but it's just a very common assumption to make. And that has the neat side effect that, at least in principle, we can model a sequence which has an infinite number of tokens in it with a finite number of parameters that doesn't grow with the length of the sequence. So that's one reason why Markov models are particularly popular, although you can relax it and allow these parameters, say, to change over time. Let's go back to this Markov assumption and see if we can understand statistically exactly what we're assuming here. And what I'm going to talk about now is how we can view it as essentially applying two different rules or assumptions. First off, we're going to use the product rule to decompose the probability in a general way, and then we're going to talk about how using conditional independence properties we can simplify our general probability of the sequence to recover the Markov model. Okay, so let's do that. So first off, let's apply the product rule to our sequence above. So we know that the product rule gives a general way of factorizing any distribution. And here I've slightly generalized it to the sequence of length t variables. Previously in the course, we've seen this written down for a pair of variables, and I'm just going to generalize that now, essentially applying it recursively. So by that, I mean, we can write down the probability of our sequence, y1, y2, y3, up to y big T, as the probability of the first item in the sequence times the probability of the second given the first. This is completely general at this stage. This is just the joint distribution over y1 and y2, and any distribution can be written down like this. And now y3 can be generated in terms of y1 and y2. y4 can be written in terms of dependencies on y. Let's keep our order consistent here. y1, y2, y3, p yt given y1 to big T minus 1. Okay, so this is the completely general way of writing any distribution. Any distribution over the sequences can be written like this. It's just application of the product rule recursively. You'll notice that this does not look the same as the distribution that's coming out of our Markov model. And so what the first order Markov model says is, let's assume that the next item in our sequence, let's say at yt plus 1, is independent from all of the previous y's, y1 through to yt minus 1, given the current setting of yt. Okay, so this says that no matter what the values are of y1 to t minus 1, they're not going to affect the distribution over yt plus 1. The only thing that affects the distribution over yt plus 1 is the current setting of yt. And that means that these distributions here don't depend on the variables shown in red here. So y3 only depends on y2, and y4 only depends on the variable y3, so on and so forth all the way through here. P yt given yt minus 1. The distributions at the start of this sequence here are correct, and although they're general, they're the way to write down the distribution for this, the first two variables in the sequence. Good. Okay, so the point is here, you can view the Markov model as doing the following: writing down a general distribution over the entire sequence using the product rule that can be used to describe any model that you choose to model the sequence with, and then applying conditional independence assumptions, which says, given the current value of the sequence, the next item in the sequence is independent from anything that came before that current value in the sequence. And then we get our Markov model that we wrote at the top of the slide. Of course, this leads to simple generalizations. And you can imagine how this goes, but a particular simple thing to do is to look at second order Markov models. Now each item in the sequence is independent from previous entries given the previous two items in the sequence. And that means when we write down the model, we have the same distributions over the first two variables, y1 and y2, And now y3 depends on variables y1 and y2. That's more general than the distribution up here, which just depended on y2. And the last item in the sequence just depends on the previous two items in the sequence. And now that means we have to add some arrows into our directed model here. Rather than each variable being connected to its immediate predecessor, it's connected to its immediate two predecessors instead. So this is now called second order Markov models for obvious reasons. So in the next two chunks, we're now going to look at two examples of this, one for situations where y is discrete and takes discrete values, and one where the y's will take real values. And because these two approaches were developed in different communities, respectively, the natural language processing community did much of the development for discrete valued variables, and the signal processing and control communities looked at real valued quantities for modeling of signals. It's going to turn out that although they're both Markov models, they're going to use kind of conflicting terminology. So it's useful to have this sort of broader view that we're presenting here to unify that terminology.